Located in the foothills of Golden, Colorado, the National Renewable Energy Laboratory focuses on finding creative answers to today's energy challenges. From breakthroughs in fundamental science to new clean technologies and integrated energy systems that power our lives, NREL researchers are transforming the way the nation and the world use energy.
We're really excited at NREL to be key partners in the Liquid Sunlight Alliance, LiSA. We believe LiSA will fundamentally transform the field of artificial photosynthesis to harness solar power to directly produce fuels and chemicals. We also think LiSA will have broad impacts across the chemical and material sciences field, as well as other energy science areas. NREL will bring distinct and diverse capabilities and expertise to LiSA that can help capture the potential benefits of directly coupling solar energy with chemical transformations. For example, we bring capabilities in the material science of photoabsorbers that include both new materials as well as tandem concepts. We also bring approaches to create and understand microenvironments for chemical transformations. And we bring decades of expertise in solar photochemistry, photoelectrochemistry, the design of solar energy conversion systems, and characterization at the materials, device, and system level.
The project includes 3 phases. Phase 1, which will focus on components making up a solar fuels generating system, from the light capture and charge separating semiconductors to the catalysts and species controlling reactant flux. Phase 2, which assembles these individual components into microenvironments, where emergent phenomena occur as a result of their assembly. Phase 2 will use co-design principles to evaluate the microenvironment assemblies to understand these emergent phenomena and lay the groundwork for designing the sequential catalytic processes needed to generate liquid solar fuels. Phase 3, which studies co-design and characterization of complex systems of microenvironment assemblies that perform sequential catalytic steps necessary for generating solar fuels, all in a monolithically integrated reaction environment.
In LiSA, we are synthesizing complex alloys of catalytically active photoabsorbers where the number of compositions to evaluate is too vast to reasonably tackle by conventional approaches. NREL has a long history of discovering and developing new photoabsorber and charge transport layers for thin-film photovoltaics. This has led us to build several state-of-the-art high-throughput thin-film deposition systems based on combinatorial sputtering and pulsed laser deposition. These tools enable us to rapidly survey growth parameters from large regions of chemical space from across the periodic table. Growth is followed by high-throughput measurement of the suite of properties required for solar fuels materials, including light absorption, catalytic activity, operational stability, and charge carrier transport. This approach will allow us to efficiently isolate and optimize the most promising photocatalytic materials for detailed follow-on study by LiSA.
NREL has world-class semiconductor epitaxy capabilities, including metal organic chemical vapor deposition, which is used to grow the world's highest efficiency multi-junction solar cells. We can use these techniques to grow complex device architectures, such as 3-terminal tandems, to drive multi-step CO2 reduction reactions to liquid fuels in a process known as cascade photocatalysis. We can also use molecular beam epitaxy to grow high-quality photoabsorber materials and heterostructures. This is a more flexible technique for demonstrating novel materials. Using these tools, we can bridge the gap between materials discovery and demonstrating the next generation of high-performance photoabsorbers for solar fuels.
NREL will use model semiconductor nanoparticles to understand the rare events that lead to photocorrosion in collaboration with scientists at SLAC, LBNL, and Caltech. This is NREL's Plasma-Enhanced Chemical Vapor Deposition, or PECVD system, that can grow a range of intrinsic and doped semiconductor nanoparticles that are difficult to synthesize using colloidal approaches such as silicon, germanium, and 3,5 such as gallium indium phosphide. This PECVD instrument uses gas and organometallic precursors similar to what you'll find in the semiconductor growth industry, just at a research scale. Our PECVD system has an intricate series of pneumatic valves, mass flow control devices, and temperature and pressure controllers that can deliver essentially any volatile molecular precursor to the reaction chamber. We plan to modify the surface chemistry of these PECVD-grown nanoparticles and leverage their high surface-to-volume ratios to allow us to understand the first steps in photocorrosion using synchrotron-based time-resolved X-ray experiments at SLAC and LBNL.
The activity and selectivity of electrochemical reactions are significantly influenced by their local reaction environment, including the composition of the electrode and electrolyte. Using operando spectroscopy and microscopy, we will probe the microenvironment of catalysts during electrolysis for a variety of chemical reactions, including water splitting and CO2 reduction. Through LiSA, we will partner with computational and experimental groups to determine the optimal local conditions to drive efficient and selective electrocatalysis.
NREL has 2 separate cleanroom facilities with a total of 3,750 square feet of Class 100 and Class 1000 lab space dedicated to semiconductor processing and metrology. Our fabrication tools include chemical hoods, mask aligners, nanoimprint lithography, physical vapor deposition, and reactive ion etching. Our metrology tools include laser confocal microscopy, optical microscopy, focalometry, and ellipsometry. We also have a dedicated silicon cleanroom with a 156 millimeter tool set for full-size solar cell processing.
Together, all of these capabilities at NREL will help the Liquid Sunlight Alliance establish a scientific foundation for next-generation solar fuels.